Hello, my name is Wang, and today I'm going to present my systematic review on the discriminative accuracy of virtual reality neuropsychological assessments for cognitive impairment and comparing it to traditional exams. This study aims to explore a new method for detecting cognitive impairment with the hope of facilitating early detection of neurological diseases. Before we dive into the study, we must first understand the issue of cognitive impairment and its impacts. Some of the symptoms of cognitive impairment include difficulties with memory and attention, prevention from adequately performing instrumental activities of daily living, and these include managing finances, shopping for necessities, using communication devices, and preparing meals. Other symptoms include fatigue and mood changes. Cognitive impairment is affecting millions of people around the world. As you can see in images to the left, there are statistics on dementia and MCI, which stands for mild cognitive impairment. For dementia, the figure is from 2019 and is currently 2025, so cases have increased since this was made. In 2019, 55.2 million people globally are living with dementia, with over 60% in lower and middle income countries. For MCI, cases are also severe, with 1 out of 10 Americans over the age of 60 are living with MCI, and with cases expecting to triple in 2050. This is why early detection is crucial to ensure that those with cognitive impairment are treated before their conditions worsen. Many popular detection tools are debated to be inaccurate, leading to investigations on appropriate screening measures. So traditionally, cognitive impairment detection tools require the patient to recall certain memories, answer questions, and perform tasks with a writing utensil. Two notable examples are the mini mental state exam, MMSE, with less than 18 out of 30 as a warning sign for cognitive concerns as a score. And another example is the Montreal Cognitive Assessment, also known as MoCA, with less than 26 out of 30 as a warning sign for cognitive concerns. Currently, its concerns are that they do not take account cognitive domains like executive, perceptual motor, and spatial function. On the contrary, virtual reality, also known as VR, is a robust technology that allows the user to interact with three-dimensional artificially generated environment. It can stimulate real-life settings and allow health professionals to access how the patient processes cognitively in relation to everyday tasks. Its concerns are the lack of research on using VR to assess cognitive functions throughout the 6 cognitive domains, which are complex attention, executive function, learning and memory, language, perceptual motor function, and social cognition. The objective of the study is to investigate the feasibility of virtual reality assessments to screen for cognitive impairment and its performative comparison to traditional neuropsychological assessments. This study is a systematic review of 11 virtual reality detection systems for cognitive impairment. A systematic review was conducted following the PRISMA guidelines. Databases such as PubMed and Google Scholar were utilized. The exact keywords for each database can be seen on the slide, but the main words used in the search were virtual reality, cognitive disorders, and assessment. 346 articles were narrowed to 11 articles, being included in the review through exclusion criteria. Figure 1 shows the PRISMA flow diagram of the review detailing how exclusion criteria were enacted. 346 articles were screened for title and abstract, with 297 records excluded, leaving 49 to be assessed for eligibility by full text. Within the 49, 28 were excluded for no mention of virtual reality systems being able to discriminate cognitive disorders and or no correlation with traditional assessments. One article was excluded for its inability to be opened in full text, and 10 articles were excluded due to insufficient or ambiguous data, leaving us with 11 studies to be included in the review. To the right are the 11 VR cognitive impairment detection systems that are analyzed in the study. The first section of the study focuses on the accuracy of VR models. All the research studies indicate VR's ability to discriminate between cognitive intact and cognitively impaired, as shown by a significant difference in quantitative outcomes between the two groups. VR Supermarket is one example of a strong VR discriminatory tool. As shown in Figure 2, models generally show excellent discriminative power, as indicated by their high AUC scores. The AUC, a key metric for evaluating classification models, is a number between 0 and 1, with a value of 1 presenting a perfect classifier. True positive rates correlate with sensitivity, which represents how much ground truth is correctly judged when it is true, In contrast, the false positive rates represent how many correctly judged ground truths are false. To diagnose the baseline, a majority of the models achieved an AUC of 1 and were able to completely distinguish between the positive and negative classes without any classification errors. Although the LR model has an AUC of 0.93, this value is still extremely high. Furthermore, strong levels of detection are also present in the VRFCAT. The assessment tested forced progressions, total adjusted time, and errors. Through all three bar graphs in Figure 3, the subjective cognitive decline population consistently performed higher values with a notable difference in all categories, showcasing its accuracy and discriminating one group from the others. Here are other examples of VR's accuracy. In a virtual kiosk test, it included tasks that concluded a notable difference between the performance of the patients with MCI versus the healthy controls. Specifically, patients with MCI had a greater error and much longer time of completion. Onwards, the CAVR is a fully immersive VR system assessing 6 cognitive domains through a realistic virtual task. It shows a promising correlation with established cognitive measures. Mean differences between cognitively intact and cognitively impaired range from 46.23 to 81.85 and 40.74 to 73.51 after education adjustments, showcasing high discrimination between the two groups. In the SCTVR, it shows high diagnostic accuracy for detecting MCI. At the optimal cutoff score of 70.77 out of 71.56, the test correctly identified 94.4% of individuals with MCI and correctly ruled out 96.4% of healthy controls, resulting in a Uden index of 09.09, which indicates excellent overall test performance for distinguishing MCI from healthy individuals. The REACH exam has an AUC of 0.821, demonstrating the model's quality in performing very well at distinguishing between the two groups. Lastly, the variable assessment also has impressive results. The assessment had an AUC score of 0.765, a sensitivity score of 0.833, and a specificity score of 0.722, which are all considered high Pearson scores. The second section of the study focuses on the comparison of virtual reality and traditional cognitive assessments. Overall, the virtual reality studies included in this review tend to showcase its ability to be as competent as, if not better than, traditional assessments. Strong correlation is present in the VRFCAT, especially in individuals with subjective cognitive decline. This is demonstrated by significant associations between higher MoCA scores and faster VRFCAT completion times, fewer errors, and fewer forced progressions. The correlation is present but weaker in young and older adults, emphasizing that the strongest link between MoCA and VRFCAT appears in those with subjective cognitive concerns. Furthermore, the VECA virtual reality models signifies a strong correlation towards the MoCA exam, with Pearson scores ranging from R equals 0.47 plus or minus 0.06 to R equals 0.9 plus or minus 0.06. Its VRAI model held impressive results, considering the highest possible value of the correlation coefficient is 1. Moreover, not only does the VSIDCS have a strong positive correlation with the MoCA, R equals 0.774, p-value less than 0.01, but the VSIDCS also has a strong positive correlation with the MMSE, with an R value of 0.795 and a p-value less than 0.01, demonstrating feasibility by aligning closely with these two widely used cognitive assessments. VR assessments can also outperform traditional assessments in sensitivity, leading to greater discrimination between two groups. In the VARBOM test, the VR cognitive test and MoCA scores are strongly related with an R-squared value of 0.415. This means about 41.5% of the variation in VR test scores can be explained by the MoCA scores after adjustment for age and medication, indicating substantial overlap between the two measures. In addition, the mean difference between the cognitive intact and cognitively impaired groups in VR assessment compared to the MoCA-K is typically greater, demonstrating the possibility of virtual reality assessments being more sensitive than traditional assessments, as shown in Figure 6. This is also proven in Figure 7, with the VARIBOM having a higher sensitivity score and discrimination score. Despite its specificity score being lower than MoCA-K, its Pearson score is still considered to be very high. And in the SCTVR model, it has a sensitive detection with a t-value of 15.157, which is greater than traditional exams such as the WAIS BDT and BOCA, with a t-value of 10.441 for the former and 10.226 for the latter, suggesting that VR could be better discriminatory tools than traditional ones. Finally, due to some systems' moderate correlation with traditional assessments, virtual reality implications can be a complementary tool, offering unique insights into cognitive and functional abilities beyond standard tests. In the CAVIR, participants classified as cognitively healthy by MoCA performed significantly higher and faster on CAVIR tasks than cognitive impaired individuals. The moderate positive correlation between CAVIR total scores and MoCA R equals 0.63, MMSE 0.55, and AMT 0.48 demonstrates that CAVIR reflects overall cognitive status well, suggesting CAVIR as a complementary, ecologically valid alternative to traditional assessments, especially in primary care settings for early cognitive impairment detection. Similar results were shown in the Bouchard et al.'s virtual environments, which held a Pearson correlation coefficient of R equals 0.45 and a p-value of 0.01 between the prospective memory task in virtual reality and the MoCA. These trends also appear in the virtual kiosk test correlation data, where the VR model was compared to 5 traditional assessments with absolute correlation coefficient values ranging from 0.28 to 0.63. Similar values appeared in the REACH assessment. Pearson coefficients range from 0.312 to 0.427, indicating a weak to moderate positive correlation between two variables. Lastly, the AGT subtest shows selective correlations with traditional cognitive assessments. Specifically, the AGTC subtest significantly correlates with global cognition, also known as MoCA, and suggesting VR tasks can reflect overall cognitive function. The interference index correlates with AGTA, showing a link between VR performance and selective attention, but executive function and divided attention did not, highlighting differences between VR and traditional tests. And here's some limitations. Education levels can factor into various VR tasks. It can be likely that those who are more familiar with technology or have a higher education background will perform higher or be more eager to participate in such studies than those who have neither quality. These constraints can make the outcomes biased. In addition, the following studies typically focus on a specific area or group of people, leaving out a large notable population. In some cases, those with hearing, vision, or other impairments were not able to participate, indicating that many VR screen tools are not quite accessible. VR studies had varying outcomes with one another in terms of accuracy, sensitivity, and correlation with traditional exams. For example, some studies had very high correlation with traditional neurological exams, while others had very moderate levels of correlation. In some cases, VR assessments outperformed traditional methods, thus certain results could have skewed data. On top of this, many argue that traditional screening tools like MoCA and MFSE have many barriers. Therefore, because traditional tools were the baseline screening methods, correlation values can be controversially debated. And to conclude, VR cognitive assessments for screening have been proven to have high levels of discriminatory accuracy. Furthermore, VR cognitive assessments have demonstrated significant correlations with a variety of traditional neuropsychological assessments, with some relations including high or moderate correlation, and even in certain cases even outperforming them. As VR has emerged as a potential beneficial screening tool, further research is needed to explore its full capabilities across different cognitive domains with a wider range of cognitive levels. Future studies should prioritize improving the accessibility of VR systems and expanding data collection to include a more demographically represented sample. Thank you so much for listening to my study, and I hope you guys enjoyed.